Hey guys, Mr. Wood here, continuing on in chapter 5, and need a couple jokes here. This will be our last video before fall break, but over fall break, I really need you guys. Just got done with that test and be working on getting ready for into chapter 5, because we're going to be pretty far through chapter 5 now. So, but anyways, here we go. What happens when you cross a witch and a clown? A brouhaha. That wasn't bad. So, okay, so here we go. We're back to where we were in chapter 5. And really a lot of review on the combined gas law, the ideal gas law, STP, and all that. So, okay, now here's something that's new, and it's not a major point, and I don't want to spend a lot of time on it, but it's about density. Okay, so we had done had done this problem. And looking here thinking we did, and you can see the problems in the book, and this would be a good thing to be doing over fall break, is to be working into chapter 5. Okay, the next thing is something that is not on the formula sheet. It is on the quiz, but it's not going to be on the test, and so I don't want to spend a lot of time on it, but I do want to kind of go through this quickly. But it's about the relationship of gas density and molar mass. So let me just show you the derivation. So again, if we were in a normal year, I would definitely include this on the test. This is one of the things that once in a while I want to get to, that is just learning chemistry, not necessarily on the AP test. But this year, because we are in this weird situation, I'm going to kind of eliminate some of those things. This is one of them. Okay, so, but anyways, this is gas density. First of all, if I know that density is equal to mass over volume, so if I rearrange that, volume is mass over density. And I'm just showing you how you could derive this. Well, I know that PV equals nRT, and so if I put this in for volume, plug that in, substitute that in, I get pressure over mass times density equals nRT. Well, then if I rearrange this for density, so if I do algebra, so I bring density up here, what I get is density is equal to the mass times the pressure over nRT. Okay. Well, this, if I have M, which is mass, over moles, well, what that is the molar mass. Mass per mole is the molar mass, and in chemistry, they always give this a capital M. So if I plug that in, then for the molar mass, the density is equal to the molar mass times the pressure over RT. And the units on the density of a liquid or a solid are always grams per milliliter, but for a gas, it's grams per liter. The density of a gas is much less. Now, we could rearrange this, and if we are trying to solve for the molar mass is equal to density times RT over P. Okay, and again, I don't want to spend a lot of time on this, and I've already probably spent too much, but just the derivation of density using the density equation and using PIV-NERD. And so with that, then you guys could do a problem like this. Okay, so it says calculate the density of ammonia. So they assume that you guys can write ammonia. Ammonia is NH3 at 752 torr and 55 degrees Celsius. Okay, so then what I could do, so if I come back here, I'm trying to find density. So I'm trying to use this equation. So ammonia is NH3. There's a couple molecules that in AP, they kind of expect you to know. This is one, ammonia. Another one that comes up from time to time is methane, CH4. And so they, again, kind of expect you to know that right there with water. Okay, so I want to solve for the density. So the molar mass of ammonia is 17. Okay, so 14 plus 3. The pressure, the problem said that the pressure is 752 torr. So for R, again, it depends on the unit, like we talked about in the last lesson. And this is where, on the formula sheet on the back, if I'm looking for torr, it is 62.36. And it is liters times torr over Kelvin times moles. And again, I got that from right here. It's nothing that you have to memorize. And then the temperature is 55 Celsius, which if I get into Kelvin is 328 Kelvin. Just like you guys can see as we're about to the fourth of the way through the class, a lot of times, or almost all the time, I always go back to units. So Kelvin goes, moles go, torrs go, and I'm left in liters. I'm left in grams per liter, which is what I was talking about, grams over liters, the units for the density of a gas. And what I get there is 0.626. The density of a gas is, of course, much, much less than the density of a solid or a liquid. Okay, so again, that's all I'm going to spend on that. But again, if you take chemistry beyond our class and we get back to normal life at some point, you guys would go more into depth on that, and hopefully again, and sometimes my whole goal is just for you guys just to be learning a lot of chemistry, just bottom line. Okay, there's another problem here, but I'm going to just again move on just for the sake of time. Standard molar volume. And so here's a thing again from first year chem, standard molar volume. The volume of 1 mole of a gas at STP is 22.4 liters. Remember, STP, standard temperature and pressure. So here is a problem that we could have done, you guys did in first year chem. Calculate the moles of 1.75 liters of nitrogen gas at STP. Okay, so to do this, there's two ways to do this. So let me erase the board here. Okay, so one way to have done this, so we're trying to find the moles. Now, to me, this is the way I always do it, the easier way. If I have 1.75 liters of nitrogen and I want to solve for the moles, because it's at STP, the problem says it's at STP, and only can do this at STP where with just a conversion that 1 mole of any gas occupies 22.4 liters. So I'm going to use that here. So I'm going to go 22.4 liters for every 1 mole. So if I take 1.75 divided by 22.4 gives me 0.0781. So again, that's the way I would do it. When it's at STP, it's just to do a conversion. But the other way you could have done this is you could have used PIV-NERT. Okay, so STP, so the pressure is 1. The volume was given to us, it's 1.75. The moles are X, and my units here, I'm going to use 0.0821, and the temperature at STP is 273. And if I solve for X, I think I get the same thing. Should get the same thing. Yep, get the same thing. So whichever way is preferable for you to do, and sometimes in first year chem, I always just tell my students, gosh, PIV-NERT's a go-to, that always works, then use PIV-NERT. Okay, so back to the notes and doing some pretty good problems here. These would have been like this next one is a problem probably beyond what we would have done in first year Chem. Okay, gas stoichiometry problem. It's a very good problem. This one would have been a little bit above what we did in first year Chem. So 2.80 liters of methane, CH4 at 25 Celsius, 1.65 ATMs is mixed with 35 liters of O2 at 31 degrees Celsius and 1.25. Calculate the volume of CO2 produced and the total volume of gas left after the combustion, which the pressure is 2.5 and the temperature 30 degrees Celsius, and assume the water in the reaction is liquid water. And I'm telling you that one place, and you guys have now been through the first test, and you know that the tests are good tests, is the problems I do in class. And this would be a classic case, and a problem something like this will be on the Chapter 5 test. So if you guys were in front of me right now, I'd say, okay, what do you do to start with here? And to start with, a lot of times the answer to that is to always write out the reaction. So if I do that, I'm going to take CH4 plus O2. And if you read this, it says that methane is mixed with O2, calculate the volume of CO2 produced, and then water. So we have CO2, and the CO2 is a gas. This is water is a liquid. Okay, and then balance it. So again, this is a lot of times, again, always a starting point. Gives me a handle on what I'm doing. Okay, now where do I go from here? Well, about the methane, it tells me that I've got, this is what it tells me about the methane. It says I've got 2.80 liters. It's at 25 degrees Celsius, and it's 1.65 ATMs. Well, I can solve for moles here, and a lot of times the step-by-step process is to write the equation and to get things into moles. And then what it says about O2 is we have 35 liters, I have 31 degrees Celsius, and I have 1.25 ATMs. So what I can do, I can go back and I can use PIV-NERT. So I can solve for the moles of CH4 by using PIV-NERT. Okay, so the pressure is 1.65. The volume is 2.80 liters. The N is X, is what I'm trying to solve for. And the R I'm going to use because of the units, ATMs and liters, it's going to be 0.0821. And the temperature is 25 Celsius, which is 298 Kelvin. And when I solve for X, the moles I have is 0.189. Okay, well, I'm also going to solve for the moles of O2. Again, I'm going to use PIV-NERT. So for O2, the pressure is 1.25. The volume is 35. The moles are X, 0.0821, and then the temperature in Celsius, or I'm sorry, in Kelvin, 31 Celsius, 304. And so what I get here for X is 1.75. Okay, so now I'm going to go back here to me. So I wrote out the equation. I got both in the moles. And I always go, what am I trying to find? Well, I'm trying to find, first of all, the volume, the liters of the CO2. There's actually a couple questions here. And that's the first thing is to find out the volume of the CO2. So I'm now going to set up an ice table. And I know that I've got 0.189 moles of the CH4, and I have 1.75 moles of the O2. And I know I don't have anything on this side. And liquid water is really not a factor here. Well, looking at these two, now it's a limiting reactant problem. 0.189 and 1.75, using 1 to 2, this is limiting, so this is gone. This is going to run out before this. It's smaller. Okay, so then the amount used here, because it's 1 to 2, I'm going to take 0.189 times 2 is 0.378. So I'll take 1.75 minus 0.378. I'll go 1.372. I know my sig figs aren't right, but we'll come back to that. And we'll round at the end. And then it's 1 to 1, so how much I would have made here would have been 0.189. It's all based off this. You know, waters were not a factor here because it's not a gas. And so water would have been plus 0.378. And again, it's not a factor. Okay, so the first question then is the volume of CO2. Okay, so I'm going to take this. I now know how many moles of CO2 are produced. And now I'm going to go back and do a pig-nerd problem. So the pressure, and it says that the total pressure is 2.50. So this is after the reaction. The volume, let's see, calculate the volume. So the volume is X. And now I know the moles, it's 0.189. And the value I'm going to use for R is 0.0821, which means, because this is in ATMs. And the temperature, it says it's 30 degrees Celsius, so it's 303. And so what I get there, X comes out to be 1.88 liters of CO2. Okay, and then the final question, it says calculate the total volume calculate the volume of CO2, so we just got that, and the total volume of gas left over. So I'm really not concerned about this. So for the total, for the volume of all the gases, so here this was the volume of the CO2. So now to find out the total volume, again, I'm going to use Pivner. And so the pressure at the end is 2.50. The volume is X. But now I want to know the total volume. So I'm going to go back up here, and I have 1.189 and 1.372. This over here, water, was a liquid. So it's not a factor. And the methane has been consumed, so it's gone. So I'm going to take 1.372 plus 0.189, and R is 0.0821. And the temperature is 303. So the trick here is there's two gases left. There's the O2 and the CO2. So I'm just going to add those together. And what I get for the volume total, so if I solve for X here, it's 15.5. So here was the answer for the volume of the CO2, and here's the answer for the volume total. And again, like I said, this is a good problem, again, to go over at some point and to make sure you're good on. And this is a kind of problem that will be something like that on the next test. And hopefully you guys can see now when I say there's going to be a problem like this on the next test, I am usually telling you the truth. Not that it makes it any easier. We do a lot of challenging problems in here. So that would be a good one to go over, a good problem there. Okay, here's another good problem. Okay, so 850 milliliter flask containing CO2 with pressure 1.44 and temperature 312, and a small amount of LiOH is added, and consequently the pressure reduces to 0.56. Determine the grams of Li2CO3 formed. Liquid water also forms in this. Okay, so here we go, another really good problem. Okay, so again, it's like in this last problem, I'm going to go back and I'm going to write an equation for this. Okay, so if I do this, if I write the equation for this, it says that I have CO2 gas, and I put in there lithium hydroxide, which is a solid. Lithium hydroxide would have to be a solid. It's a being an ionic compound. It says it makes lithium carbonate, which also has to be a solid, and water, which it says is a liquid. Again, just like in the last problem. So then I need to go back and I need to balance this, and I think I just need a 2 there. So again, writing out the equation. Now this one's a little bit tricky, but the key here in this problem is that the pressure drops. The pressure goes from 1.44 to 0.56. And so that has to correspond to mean to the moles of CO2. It's the only gas. So 0.88 would have been the moles of CO2 that reacted. The problem, what we're trying to figure out, are the grams of the Li2CO3. So what I'm going to do here is I'm going to go back, and it told me that the temperature is 312 Kelvin, and it said that the volume was 850 milliliters. So again, the trick in this problem is that these are the units of pressure that reacted. Okay, so that tells me then this is what I'm going to use, and I'm going to do PIV-NERT, and what I'm going to do is I'm going to solve for the moles of CO2. And once I know that, then I can do stoichiometry and find the grams of the lithium carbonate. So the pressure is 0.88. So that was what reacted. The volume is 0.850. Moles are X. R, again, is based off of the units of volume and pressure. The temperature is 312. Okay, so if I solve for X here, which will be not my final answer, but it'll be the moles of CO2. X it gives me is 0.0292, so this is moles of CO2. Okay, now I can do stoichiometry and I can go to lithium carbonate. So there's 1 mole of CO2 to 1 mole of lithium carbonate. Final thing is I find the molar mass of lithium carbonate, 73.9. So that's the mass of lithium, carbon, and 3 oxygens. And That gives me technically 2 sig figs, 2.2. Again, that is another really good problem to do. So that is a good place to stop going into fall break. And we get back, we are well now into chapter 5, and we're definitely into some very challenging problems. So be looking, guys, through chapter 5, be working these problems, and hopefully you'll have a restful fall break. But I know this is a tough class, and feel free again to ask questions and anything I can do to help. So talk to you soon.